Good morning. Welcome to episode number 35 of the ZoomTown experiment. This video is going to be very different than anything I've presented thus far on the ZoomTown experiment. I would like to say that it's all good news and everything is peachy keen, or the bee's knees perhaps. But in this case, boy, things aren't going real well on the ZoomTown experiment. Just a quick side note, about a month or two back I started listening to an artist. She's a country artist, typically not my music style, but it's Lucinda Williams and a song called American Dream. And the one part of the lyrics that repeats over and over and over again throughout the song, everything is wrong. I swear she's been talking to me and I never knew it. Yeah, a lot has gone wrong in these last few weeks since the last story. I think it's been probably 3 weeks, maybe 4 weeks now since I filmed our last episode dealing with the TCRT 5000 photoreflective sensor. Came up with an idea how I could use that sensor to detect more information. Turns out that's a really important thing I came up with relative to where we're at now. Now, before I go into all the doom and gloom, I'll tell you what was happening after filming that story and how I started working on the next story. As you know, I needed to start working on encoder steering to get around turns. And a big part of this whole project since the beginning was that I would use line following for all straight line moves where possible and encoder steering for all turns. Well, that was a neat idea when I came up with it, but it sure isn't working out well. I spent a tremendous amount of time working through a lot of problems with getting the Zoomie to start a turn and end that turn at exactly where I wanted it. I'm looking for about 1 millimeter of accuracy for target position. That's in the English world, that'd be 0.04 inches or a little more than a 32nd of an inch, or a 3/64, somewhere in there between that. So it's a very accurate demand I'm putting on this system and methodology. Well, I ran into problem after problem after problem. And a lot of this testing started with my original prototype Zoomie, which was this guy here, I think. Yes, it's got the red wheels still. This was the original one with the homemade circuit board in it and all that. So I really got to thinking, this one is pretty sketchy at best with a lot of the wiring and so forth. And so what I thought probably would be best is if I built a new one with the manufactured circuit boards. These I sent out and had manufactured. This one here is for the logic, and this one here is the power supply. Had built the next one, which would be this one here, and started having, I won't say I started having, my reliance on that encoder feedback became very critical at this stage, and I could not get reliable positional feedback. Now, what I mean by reliable, again, is an accuracy of 1 millimeter over any turn maneuver. Some of my turn maneuvers are just a 90-degree turn, all of them are, but only at a 2.5 inch radius, which would be about 50, 60, about 65 millimeters, or a 6.5 inch radius. Even pivot turns were not working out well. So I messed around with the encoders and the wheels and the motors and everything on this one, and I thought, you know what? Maybe something's goofy with that one. So I then built Zoomy number 1. This would have been, by the way, coded as Zoomy %. This one's coded as Zoomy 1 and Zoomy 3. These two are about as identical as I could possibly make them. All of them behaved differently to some degree. Some of it I would expect. A lot of these parts are economical, low cost, so I'm not expecting the motors to be exact and all that, the gearboxes and the motors. A lot of the things I'm putting a very high demand on what I want out of them. But nonetheless, it was just everything, one thing after the other, more problems kept mounting. And that song, "Everything is Wrong," just keeps repeating in my head. And all the way up until, I'll be pretty frank on this, about a couple of days ago, I finally made the decision it has to be done differently with what I'm trying to do. Now, in the course of the last 3-4 weeks, I've done a tremendous amount of testing and trying this and trying that. And so that led to this story and what I'm going to reveal to you today. It's going to be rather lengthy. It's all discussion. I'm going to be putting slides up so that you can look at you read the text as I'm reading it to you, so that you can kind of follow along a little bit better. But the objective of this video is to set the stage for the new direction I have to go in. And that will have some consequences. We'll get to that at the end. So first thing up, let's just dive into the very first slide. And I'm calling it a reality check, and it sucks. Yes, I'm very disappointed in how everything came together at this point, but reality is reality. This is a very large experiment. I knew it would last about a year. I knew there would be a lot of problems. Otherwise, I wouldn't have done it. If I would have knew the outcome, why would I have even started on this? Unfortunately, they all just seem to hit me at the same time. Well, here's some of the bullet points. Getting the wheels to rotate proportionally to each other to make a turn. That's very key. I need my turns to be accurate, and the encoder feedback is what directs that. The distance traveled varied when line following. I could never figure out, I would put the Zoomy at the start of a line, have it run down, and I would get different readings between the left wheel and the right wheel, and getting it to end at a consistent endpoint was always confusing. I could never figure that out. Oftentimes it wasn't a lot. It had been a couple of millimeters, maybe 3 millimeters, sometimes a lot, 6 millimeters or about 1/4 of an inch. Line following at times would be unpredictable. I had good performance. I could follow the line nicely, but anything that would interrupt it or cause any deviation, it couldn't deal with that very well. And that was, of course, a huge problem. So at this point, I'm considering encoder steering just simply, to this point, is not consistent or reliable. And as I just mentioned, the different Zoomies behave differently, and in some cases by a lot. All in all, that makes localization impossible with this system, and that is critical. Think about it. I've got 16 Zoomies that'll be running around over there on that course, and the system as a whole needs to know where each other are, or it will definitely, you'll have one Zoomy turning in front of another, one backing out of a driveway, broadsiding another one, all of that. And so my demand of 1 millimeter accuracy is a pretty stout demand, very difficult by any measure with any technology that we have today. So I'm really pushing hard to achieve something that is really potentially not even possible. But I do have to get this localization in control for any of the simple stuff. Imagine driving down a road and I need to turn into a driveway at a 10-inch position. Well, if I'm at 10 inches and a half, or any other deviation from that, when I pull into the driveway, I might be pulling up onto the lawn or bumping into the Zoomie in the parking space next to it. Localization is critical to this whole experiment. While experiencing a lot of these problems, I just started jotting down everything that I thought could be a problem, causing all these different issues. So I'll just go through this list real quick. Wheels not round, wheels not consistent in diameter, wheels wobble too much. Sensor mounting positions are not consistent. On the TCRT 5000 especially, but also the encoder. The TCRT 5000s, are they too close or potentially too far away from the surface to get good readings? Is the encoder mounting too flimsy? If the encoder's wobbling around while it's moving, I could get variations in readings. Encoder mounting distance is perhaps too far from the magnet. Maybe the encoder can't read the pole movement on that magnet as it's rotating. Encoder not mounted or being mounted on the center with the magnet. And that's very critical because as the wheel rotates, if it's off center relative to the sensor, the data that the sensor would see would be, so to speak, oval shaped as opposed to round. The motors are not running at consistent speeds. I say they're always varying. That's actually a very small amount that they do vary, but each motor runs at a very different speed from the next. And I'm going to say that's probably as much as maybe 10% in my worst case motors. The other thing that came into question that I was thinking about were the 18650 cells, or the power supplies, are not delivering consistent power. Perhaps as the voltage drops on the cell, maybe the current or the voltage going through to the different components is changing. Acceleration routine is not performing smoothly. It's often slowing down a little bit too early. And it was really good and then it changed, but there's a lot going on with several different influences to velocity. So I had to really give thought to that. Moving on, velocity control could be causing positional errors due to erratic feedback. One thing I noticed, and as you know, I love doing or plotting out data using a spreadsheet, because if you just look at the numbers, it's sometimes hard to understand what that data is also telling you. If you look at a line plot of the data and see a lot of very erratic numbers, up, down, constantly changing, well, that's a big problem into itself, and we've encountered a lot of that in some of these graphs. I also am looking at encoders may not be reading reliably, and that could be causing positional errors. And that could result or manifest itself in line following and encoder steering and typical turning. PID implementation's not correct. As you know, I've used primarily just proportional, or even not technically a true typical or classic PID implementation for other feedback. So maybe that's causing the problem. So I might not be getting accurate feedback data, or I'm not implementing a good control over or with that data to control the motors accurately enough. Is the code too complex? Can it be simplified to be more robust? One thing you've noticed, I don't write a lot of MicroPython code in the very classical sense. My beginnings in programming go back to the very early 80s, if not technically the 70s, and I like a different style that I've been using for, I guess that's 45 years now, give or take. So I do tend to get a little more verbose in a lot of my code, which can make it run slower and perhaps not as elegantly as we would like. And so I have to give considerations to that. Maybe my code is getting too complex in lieu of readability. I like code that's readable. Like this project, I might go 2 months where I don't do any coding on it, and then I got to drop into it on a Saturday morning and create a story. So I need readability so I'm not spending hours and hours trying to figure out what I did in that code. Another thing we had discovered that the deterministic loop had problems that were hidden, but revealed when I did a further investigation into it, and that was caused by the garbage collector. As that garbage collector goes through and cleans up a lot of garbage, it takes a lot longer. Well, with some trickery that we had done, or better programming, I guess, in that episode where I talked about the garbage collector, I think that was 2 episodes ago, if I call it more frequently, the spikes or peaks in, we'll call it random intervals where it collects a lot of garbage, became very minimal, just over 5 milliseconds. Well, I never did correct the main loop time at that period of time because I wanted to further observe what was going on with it. We'll talk about that again in a minute. And then finally, it's very easy to try to blame hardware, especially with some of what we're using here, these motors that I'm buying, the encoders, a lot of this stuff. It's unimaginable that it's even possible to sell it for any amount of profit at the amount I'm paying for it. So I do always question the quality of componentry that I'm using. Heck, I'm making my own circuit board. Things of that nature can all be very problematic. Questioning the Pico W, I got a lot of faith in its capability unto itself, but not all Picos and Pico W boards are made by the original foundation, the good people at Raspberry Pi. So if you're getting an off-branded one, well, that could create a problem, so to speak, with perhaps low quality components creating or influencing errors as well. I really want to back burner that whole concept, though, the belief that there's something wrong with the Pico Ws that I'm currently using. And then finally, the componentry I'm using on all of the builds, I mean, heck, 3D printed off of a very inexpensive 3D printer, all kinds of components bought from places not commonly known for very high quality componentry. So everything there is always in question. Okay, now I know this is dragging on a long time here, but hopefully you understand, you'll get an understanding of how involved these big projects and big experiments can get. Moving on, I needed to remind myself of what this experiment is about and the complexity of it. I've already mentioned localization is not a trivial task. SparkFun just introduced a sensor to do this, and it's a very expensive, it's I think $75, and it cannot do millimeter accuracy. And so when you start thinking in terms like that, this whole Zoomy doesn't cost $75, and that very good, very specific sensor designed to do exactly that can't achieve what we're trying to achieve. So not an excuse, it's just an awareness statement. This is not trivial. Velocity control coupled with positional control is also not a trivial task. We are not using the most precise components to get accurate positional output from that motor. We've got a gearbox with a lot of backlash in it, very sloppy. We've got 3D printed wheels that are not round, and I can measure that and verify it. And they're not perhaps centrally located on the axle. And I'm using O-rings from a questionable source due to the amount of cost they were. So there's pre-built problems in the system, and they're revealing themselves to us right now. And it creates a problem for our position, which we know is very important. Accuracy requirements exceed the capability of the components, and that's kind of summarized with what I just said. I'm demanding a lot out of these components, far more than they were ever designed to use or do. So, plain and simple, I have to reevaluate, right? So a new direction is needed. I need to reevaluate all the components, either repair them, replace them, or remove them from the system. Makes sense, right? If I can fix it, fix it. If I can't fix it, I got to replace it with something better. And if there isn't anything better that I can afford, I need to just simply remove it and move on to another methodology to replace that component and its function. I need to reevaluate all the code. Is it too simple? Am I minimizing the effort to make the code robust enough to handle all the different problems we're encountering? That would be too simple, right? If it's too complex, maybe I'm spending an ungodly amount of time making all these calculations of which aren't needed, or that just simply mucky up the system, making it more complicated than it needs to be. And finally, the one thing you've heard me talk about this entire project so far is how fast is the code running. And we've monitored that very, very closely throughout the entire project up to this point. Obviously, it'd be great if it could run 10 times faster. Would it be any better? Not necessarily, because a lot of the errors we're seeing at a 5 millisecond resolution time slice or cycle time, we're almost seeing the data too quickly to make good evaluation of it to change the output stream. So I think we're fast enough on the code. It always has to be considered, though. And then finally, has every possible method been considered to alter the outcome? Have I really looked at everything, evaluated it, considered it, or otherwise tested it? And that's the creative and fun process of programming and projects like this. You start with an idea, you run into problems, and now you got to get creative to solve those problems. As I've mentioned before, and 6 months ago or so when I started this project, if I knew the outcome, I wouldn't waste my time doing it. What's the point? This is an exercise in exploring, being creative, solving problems, and then sharing that outcome with you folks. Now we're going to get into a little bit of backtracking of what I've covered in the last few weeks. I've clumped together some of the problems that I've wanted to consider, and then presented that in a method where what I've done with the problem as I see it, and then how I could try to solve it, and then a very brief summary of what worked and what didn't work. Here are some of the considerations or problems that I identified about 3 weeks ago. Wheels are not round. Wheels are not consistent in diameter, and wheels wobbled too much. To what effect, I really didn't know, but I did know there were variations. They were printed on an older, it's still a very good 3D printer. I think it's the Creality Ender 5 Plus. But it is getting a little bit long in the tooth, and frankly, I'm not keeping it in tune very well. But anyhow, I'm looking at those problems, I'm measuring what I'm getting, and I'm thinking, I got to come up with a more accurate wheel. So the considerations were to buy manufactured wheels. I couldn't find any in the size that I needed, so that was out of the question. I do have a CNC lathe and I do have a CNC router, and I have other manual machining equipment for both metal and woodworking. So I could machine them from aluminum and then wrap the O-ring around that, and most likely it would be more accurate. I'm keeping that concept on the back burner for right now. There's a lot of work and effort that goes into it, and that requires a lot of time. So I'm kind of holding that solution in reserve. The next idea I came up with is to get a 3D resin printer and print them. Resin printing often has less errors or less dimensional inaccuracies than FDM or filament printers. So that was really my leading solution until I ran across my latest acquisition, which is the Bamboo Labs X1C, I think, printer. It's a very, very nice printer. It's very expensive compared to a lot of the other equipment out there, but it is far more capable and certainly far more accurate. Now, if you remember or may have noticed, the older Zoomy that I've been playing with had red wheels. The new Zoomies have green wheels. Color has nothing to do with it. It's just how I keep track of which ones are new and old. And the green wheels are off the new printer. They're much more precise in diameter and consistent and roundness. They're not perfect, but they're much better. I made them slightly larger to get a little more stretch on the O-ring in hopes of evening that out. The center hole, the D-shaped hole that fits on the axle, was far more consistent, so it fit on the axle more snugly and more squarely, so I didn't have as much wheel wobble. Are they perfect? Oh, far from perfect. From my world of CNC machining, where my idea of perfect is measured in microns or tenths of a thousandths of an inch. So we're somewhere in between there, but nowhere near machined out of metal. So anyhow, those were the considerations. So I purchased the new 3D printer. It improved accuracy substantially regarding roundness, diameter, and runout. Ultimately, it had little effect on overall system performance. Next up was center mounting positions not being consistent. And I noted the TCRT 5000 especially because I was having trouble with line following. And the other possibility would be that the TCRT 5000 sensors were either too close or too far from the surface that we're reading. And that can create a number of problems there with inconsistencies from one Zoomy to the next. And if the sensor's closer to the surface, I get a different range of readings than if it's further away. So there's several different influences that come about from that sensor position. This is a very early version of my sensor bracket, and it was just a rectangular hole that the sensor would push into, and then I would just kind of eyeball it and hope friction held it in place. As time went on, this was the second iteration. I beveled this area out more and tried to create a shelf to allow the sensor to come up to a point and then stop. Better registration for position this way. And ultimately, this is where I ended up with, slightly modified in there. Off the new 3D printer, it's much more consistent in size. The surfaces are smoother, and I went with white instead of silver or black in hopes I could get better consistency on the light casting from the infrared LED. These changes certainly helped. I think line following improved quite a bit, but there were many changes I had implemented affecting line following in these past few weeks. So I'm going to say it did enhance the capability of line following substantially, but the caveat is other things changed as well. Moving on to the encoder mounting, and let's take a look at what I had first. This was pretty much the beginning all the way up till the current version. There's a very weak area right in here that allows this to flex very easily. The hole wasn't tight fitting, the opening for where the encoder fits into here, so there were a lot of little things I could do to enhance that. This is the newer version now, and you'll see I added this gusset here, and it's a little bit thicker, and that helped make it much more rigid, so I could count on that sensor not moving around or wiggling and wobbling while the Zoomie's moving along. But let's take a look at what my thoughts were. The encoder mounting was too flimsy. Encoder mounting distance was perhaps too far from the magnet. Encoder not being mounted on center with the magnet, that could be a huge problem. Both of those issues. Too far away, it can't sense the magnet, and if it's not on center, you get oval-shaped readings from it as opposed to circular-shaped readings. Sounds kind of weird, but it's a magnitude issue. And then too much backlash in the gearbox could have been causing problems with encoder accuracy and readings. And finally, the encoder is simply not accurate. So I had to look at all of that as potential problems. The one thing, hopefully I can make this visible on camera. Let's see. Okay, right there. See how I can move the wheel back and forth like that? Now, the encoder reads that. And I'm not rotating the motor or the gearbox. That is just the backlash in the gear train. And that created all sorts of problems in this process of reading the encoder and seeing strange little movements or very large movements if I was at the rollover point on the encoder's absolute 0 point. It creates a lot of trouble. So, I had to really look into this one. Some of the considerations were design a new bracket. We already talked about that. Test the sensor for more optimal position. Well, I actually went through and measured it very accurately using feeler gauges, and that isn't the case. I wanted to consider a different motor. Well, these are inexpensive, and they actually made this project possible because of their cost. So finding another motor in a comparative cost range is very difficult. Same thing with the encoder. Now, interestingly, here is the same motor, but this time you'll see that the encoder is mounted on the back. My encoder is out here on the wheel and at the far end of the output shaft. So this encoder reads the actual motor rotation, where my encoder, the way I've constructed it, reads the axle or output shaft rotation, along with all of its backlash and problems inherent in that. But this combination would work. It will fit in the current Zoomie design. I would have to modify a lot of stuff to get it in there. But ultimately, it's a cost I just can't afford to incur. I put a tremendous amount of cash, well, tremendous, about $1,000, maybe even more, in this whole experiment. And at some point, you just kind of got to set the mark. You know, let's not exceed this. Financially, just as a side note, this video series has been a financial bust for YouTube revenue. If it were not for the very generous people doing the super thanks, it would even be far worse than it already is. I'm not complaining. I'm not asking for money, nothing like that. It just helps defray the costs. And I do very much appreciate those super thanks. It definitely helps. So with all that said, the bracket was redesigned, printed a new one, locates the sensor more consistently. Nothing can be done about backlash. It is what it is. You can't fix that on these motors. And I just talked about that motor, the same motor with an encoder on it, but it's cost prohibitive. So the new bracket is more rigid. It improved registration slightly, and the gap space is more accurate because it can't wobble as much. But I saw no real quantifiable improvements based on that. Another thing that I had noticed is the motors are not running at consistent speed. It does go up and down, up and down. Even if the PWM signal is a constant, the RPM does vary slightly. But think about this. Our wheel at the diameter it is, I get about 5 inches, that'd be 125 millimeters of travel for every rotation. Well, if the speed of rotation changes, well then so does my distance traveled. So varying speed is yet another thing that we have to combat in code so that I maintain proper position. So it's another influence to our system messing with our output of accurate positional movements. Then different motors run at different speeds, even if they are at the same voltage. And that means that if I've got two different motors in one Zoomy, one wants to run faster than the other, I'm constantly fighting it with our PID routine for steering. So I had a look at what could be, how to deal with those issues. Went back to the 18650 cells and the power supplies, potentially not delivering consistent power. Alternative motors that could be of higher quality, motor variations on what I've got here, and then problems with the gearbox. Well, overall, through my investigation on that testing, the power supply system is very stable, even as the cells run down, and they take a long time to run down. So to verify that that wasn't the problem, I also took one of my bench power supplies, ran power leads over to the test track, ran off of that as the power source because I know that power and current would be consistent throughout a whole day or even several days of testing. No discernible information found there, good or bad, for the cells or my power supplies. So without excessive costs, I really don't have an alternative to these motors. I really kind of got to stick with them. But the one thing I did find when I was checking the motors, what could be different? Well, the easiest thing to really check would be current draw, which isn't very much at all. Less than 1/10 of an amp, probably even less than that. I don't remember off the top of my head, but very, very minimal. But how much resistance the motor actually takes sitting static? Well, that range was from 23 ohms to 31 ohms, difference between about got to be close to 20 motors, I think. That's a lot. And I swear one of them that I had checked early on in this whole thing was around 40 ohms. So if you go 23 to 40 ohms, that's going to have a huge impact on motor performance while it's running. So nothing I can do to really fix that other than maybe add an inline resistor, and that's starting to get a little on the weird side in my thinking. The gearboxes I found all had dirt in them, and I had already blown them out with compressed air, so I rinsed them off thoroughly with solvent, blew them off again, ran them on the bench, holding them so I could feel if there was chips or dirt going through the gears, and never found any more after that. Put on a light oil, and all of that really resulted in little to no improvement. Next up were some coding issues or code areas that I was concerned about. Velocity control could be causing potential errors due to erratic feedback from the encoders, so I had to look at that. Furthermore, PID implementations not being correct, or feedback data not being accurate, or motors that simply cannot be controlled accurate enough. Those were serious considerations. So all I could really do based on those concerns was to try velocity feedback for PID instead of just positional feedback, meaning I'm going to, instead of act or react to the position data, I'm going to react to the velocity. If the wheel's going slower, I got to speed it up, and that should keep it going straight as well. Then I would also try a full PID implementation instead of just proportional and derivative or just proportional. Velocity feedback proved problematic due to the erratic velocity data, cause not fully understood yet. And what I mean by that is I was getting very erratic data and I couldn't understand why that varied so much versus the positional data, because the way I got to calculate the velocity is to take positional data over time. So the time element in there made me start thinking about the earlier concern about the deterministic loop not running consistently or the garbage collector influencing that as well. So that's how I ended up going down that rabbit hole. As far as that, I don't think velocity feedback was the smart move, and it proved wrong. I also implemented full PID in line following and encoder steering, and also tried just proportional and derivative. I am unable to determine controllability of the motors to the degree needed, meaning these motors are great for what they're designed for, but there is a good possibility I simply cannot control them accurately enough to do what I want. I have to keep that as a consideration. Overall, much improvement has been gained with line following, again, referencing other improvements based on all the changes made. But encoder steering has shown minimal improvement and continues to be a problem. Next consideration, again, code. Is the code too complex? Can it be simplified to be more robust? Considerations that I focused on were encoder processing, taking the reading from it and processing that into a numerical value that I'm referring to as position data. Is the code too complex on line following? Is it doing things it shouldn't do, creating problems? Encoder steering. Just using proportional control for the steering. Is any of this just too complex or not robust enough? So with digging into that, the encoder reading has been simplified a lot in the current code base that I'm using. And if you were paying attention, you'll notice that in the previous version or earlier versions that you've seen, the encoder gives you an absolute reading from 0 to 4096 as the magnet rotates. So it's always going 0 to 496, 0 to 496. And I was taking that data and just measuring from one time to the next how much it changed and working on the amount of change every time I've read it. That way it would behave more typical like that of an incremental encoder, something that I've used a lot over the years. Problem is that can introduce a lot of errors because of that computational process at different times. It's time dependent, plus the backlash in the gearing. If the motor isn't necessarily, or the zoom isn't physically moving, I can still get readings on those tiny little movements that can cause all kinds of problems. If it rolls backwards, rolls forward, in that backlash area, that's going to add to those counters. So I switched all that to the methodology where it's almost exclusively now all absolute reading. I read the position of it. I do have to reference a 0 point, so to speak, an offset 0 point. And then every time it rolls over, I add a counter, add a value to a counter to account for each rollover instance. So It's mathematically simpler, and it provides a more absolute or a more truthful reading as opposed to changing it into the incremental world. But after doing all of that, I believe it has improved. I think it probably could have eliminated errors, but there was no problem found causing any positional errors in readings through all my testing. Line following was simplified in code volume, meaning I made it more concise, but the complexity was increased in the form of PID control, full PID control, and overall, again, performance improved greatly. Encoder steering has been modified numerous times, and there has been no appreciable improvement. And a lot of that has to do with a very fundamental problem with it regarding heading. And let me explain that here with one of the zoomies. Now, I can get the zoomie to run straight for an overall distance, say from here or to here. And it'll pretty much go straight. It wags its tail a little bit, as I've mentioned in previous videos. Even line following does that. It's just corrections in it. Now, if I need to get to that being my target right there, if I need to get there and I can drive in a straight line, great, except for one thing. If I am off by this much at the start of that movement, it's going to go in a straight line at that heading. So instead of ending up here, it ends up here. So that start point is absolutely of paramount importance. I cannot overemphasize how important that is, that starting position has to be at the perfect angle or perfect heading to get to its destination. So not only am I fighting everything else, that is another thing that has to be fought off. Now you think, okay, well, so what if it's only off by a teeny bit, a half a degree, like it is probably right now? In that distance, that ain't a big deal. Over there, that's, I think, 2 meters long or 96 inches long. That could be inches off by the time you get down there. So this is a huge problem that has to be dealt with. So as far as no appreciable improvement, it may be going a little bit straighter than it was before, but I still can't get it to go to correct heading direction no matter what I do with this particular process. As mentioned earlier, I questioned the deterministic loop not functioning properly, and were there any new problems presenting itself with the garbage collector? Well, the only thing I could really do is just simply monitor it, the cycle time of the deterministic loop. If that's changing, that would tell me, well, something would cause it. And thus far, the only thing we know that violated my cycle time limit has been the deterministic loop. So I just ran tests after tests with it, and really wasn't concerned about how the zoomie was moving, just that I was getting a consistent, updated now to 6 millisecond loop time, and there was no deviations from that. So nothing definitive in the results that from those experiments and tests. And getting back to the Pico W being unreliable, or the test zoomie having bad components, could it be a lemon? Well, I got to be realistic. I don't believe there's any problem with the Pico or MicroPython, at least nothing that I can get to repeat. Of course, there's little weird things that happen in code that I don't quite understand. Even if I'm doing the same exact thing elsewhere in the code, I can't get these things to repeat to a point where if I boil it down to a small enough demonstration program, I can get off to the good people to say, hey, look, this doesn't work. It's a bug. I've never been able to do that. So I always have to look at the problems really being on my end. I also believe it was highly suspected that there'd be big differences between the zoomies when I built the second one, and it performed very differently than the first one. Concerned, 2 more were built, and they too demonstrated differences in performance. I already mentioned that, and I just think that's realistic. I've got to expect that. And if you remember, I created a separate file for anything that's unique to a given Pico. I would put stuff in that profile data file. And so if I have to put PID tuning in there for a specific Zoomie, I can still use the same source code in each Zoomie, but it would be tuned by the data in that data file. At this point, we're going to review a lot of my analysis and what I think has to happen from this point forward. The original concept was to use line following for all straight line moves and encoder steering for all turns. At this time, I do not believe this is feasible, as every effort so far has proven that encoder steering cannot place the Zoomie to within 1 millimeter or 40,000ths of an inch of the target. I could continue to keep trying, but I do have other things I have to get to as well, so I've got to draw the line somewhere. Next up, reliance on the encoders to provide accurate positional data is believed to not be reliable or even feasible. As the Zoomie is steered, positional feedback tracks every adjustment, meaning that every time there's a little movement or an adjustment in steering, that will change its positional location. So it'll always be wrong if there's any steering, and there's always going to be steering adjustments. Regardless of whether it was line following or encoder steering, the position being reported is almost never accurate within 1 millimeter. And you would think that's very surprising on line following, because you're just following the line. You're going in a straight line. That's it. But it's doing a lot of steering during that whole process, and that's what throws it off. Furthermore, just as I mentioned earlier, if my line is here and the Zoomie is not coming into it at a straight line, actually it's got to come into it and then turn and then continue on. That actually can add a ½ inch or more of travel, 13 millimeters or more of travel, to one of the wheels over the other. That's actually how I discovered how bad that problem was. So dealing with it is challenging. We'll use that word. A new approach and a methodology that I've got to give credence to reduce the reliance on encoders as much as possible. More motion will have to be done using line following. To reduce errors produced while turning, one-wheel pivot turns will be used wherever possible. That will eliminate the proportional control needed for two-wheel steering, and that greatly minimizes the math. And with just one wheel being controlled, the probability of errors is cut by 50%. So you can imagine a large, graceful, sweeping turn over a 6.5 inch radius, 160 millimeter radius, as we go around that turn. Well, if I'm constantly checking one wheel to the other, that they're in proper proportion to each other, it's constantly making little steering maneuvers. Throughout that whole process, its absolute heading is going to change. So when I get to the end point, it's going to be very difficult to be at 1 millimeter accuracy. So I'm just going to accept that as fact and deal with it in the code. So a new approach and methodology. And this is all to improve accurate position tracking and feedback. A hybrid system will be tested, and I've already started it. This new system will utilize the concept presented in episode 33 using the TCRT 5000 for more than just line following. To facilitate the current positional feedback system, there will be markers, white stripes, placed at specific intervals along all straight road sections. These markers can be read by the TCRT 5000 and used to update the current position of the Zoomy along any road. Assuming the spacing is 1 inch, 25 millimeters, this would provide very accurate localization down to 1 inch along any path. Between each marker, the encoder data is used to provide the fine detail, the fine little measurements in between each 1 inch marker. With only being responsible for a 1 inch distance, the amount of error provided by the encoder feedback would be substantially smaller than the cumulative errors over 90 inches or 2 meters, 2.5 meters, whatever that works out to. So I'm using the encoder, going to use the encoder just to measure within 1 inch of travel. That minimizes much of the cumulative errors. And then every 1 inch or 25 millimeters, I will reset my counter at that point. And that way, all I'm getting is a small amount of error from the encoders or anything else that's going on, steering, etc. So theoretically, it should work a lot better. I'm going to put a diagram up on the computer screen to quickly show you what I'm referring to here. This is an overhead view of the Zoomy, and this is my the white and light gray stripes that currently run along both the test track and ZoomTown. This crossbar here, and here, those are white stripes, as I used in the last episode. But this is how I plan to utilize it. I can calculate where the sensor reads the start and end of the line. From that point, I can pick a point in that range where I want that to be my reference point. From there, I know the distance back to the center line of the wheels, which is critical because that's really what I need to have in a specific position when I either start or stop a move, or when, most importantly, when I'm making a turn. And that's what I'm showing over here. Now, all of this we'll get into in much more detail in the next few videos that we'll be doing. So, it's been a heck of a 3 weeks here. I got a lot of colorful language I could share with you describing what I've gone through, but we'll save that so that the censors don't shut down the video and take it off YouTube. But again, it's very frustrating to go through, especially when everything went bad all at once. Not the first time it's happened in some of my bigger projects professionally and for fun. But it is a matter of dealing with it and trying to find an alternative approach to accomplish the goal with what you've got to work with. And that can be very difficult, very challenging, and a lot of fun. So I'm good with that. The way this is going to play out, at least for the next few episodes, and I'm going to make a point here, the next few episodes, which means I might not be able to hold a weekly publication schedule. Every time I say that, I always do, but right now there's an awful lot going on with this whole project that I got to pull together very rapidly. But I'm going to have to go through, we'll do some repeats, so to speak. We're going to revisit line following. We're going to talk about this new encoding system, this hybrid methodology for localization. We've got to get those two covered really good, and then from there we can get back into working on turning. So kind of taking a couple months back step here, but we've got to get this working before we can get anywhere near the final part of this experiment. Now, I do got to call out to a couple of guys. Juan and Tomek, you both offered help and assistance. I may be pushing things off to you. If I can, it's very difficult right now because virtually everything in this entire program I kind of got bouncing around in my brain, and I'm not able to document it efficient enough or accurately enough where I could say, hey, Tome, could you do this one for me? Or Juan, could you do this one for me? It's very difficult to be able to convey all that information in the way it would have to be for you to help. But I'm sure there's going to be tasks that'll pop up, and I really, really appreciate both of you offering to help me with those tasks. I hope we can continue doing that, and other things will come up along the way for the rest of this experiment. So thank you so very much. I really do appreciate that. But we're going to move forward, see how it goes, and I'm going to try to get out these videos as fast as I can, and hopefully we'll have some more good news coming up real soon. Thanks for sticking with me. To everybody who's still watching this, obviously my viewership, I don't think I've probably exceeded 300 views on any one of the ZoomTown videos so far, and I probably get about 30 cents for that. So definitely not a labor of making money. It's a labor of love and my passion for sharing. So thanks for sticking with me, and hopefully things will get much more interesting very soon. I look forward to seeing you in the next video.